Hello, everybody. Today, I'm going to talk to you about a new dimension in geometric camera calibration. So geometric camera calibration is essential. Whenever you want to measure distances in images or you want to detect objects, you need to correct your image geometrically. You also want to compensate for very high distortion levels, especially for cameras with a wide field of view. And also, you might want to accurately align stereo cameras to each other. A distorted image may look like what you can see here on the right-hand side. The aim of the whole process of geometric calibration is to characterize that distortion of the camera system, so lens including the sensor, and to feed that characterization parameters that you get from the characterization into a correction software that automatically corrects the image before you do any other type of evaluation. And there is a more or less de facto standard called OpenCV that is commonly used for that type of image correction. The current methods that exist out there use regular pattern, and most of them use test chart. So it's a test chart based method. That often requires large charts, especially for cameras with a wide field of view. And if you want to do this at infinity, you may want to use a relay lens, but that relay lens also introduces distortion and needs to therefore to be characterized and to eliminate it from the measurements. So a test chart based method basically requires a large lab and a large setup with your camera and test charts. So we were looking for something that would work at infinity, that would work for cameras with wide field of views and in a very compact way. That's how we came up with the new approach. It basically makes use of a laser system. The laser is fed into a collimator, and that collimator illuminates a diffractive optical element. The camera under test then captures an image of that diffractive optical element and produces that image of a grid of light dots. So that's what it basically does. It creates a grid of illuminated dots, very fine dots, distributed over the imaging field. Those dots virtually originate from infinity. So you do the characterization under or at infinity. The whole thing is translational invariant, so you can move your camera left and right, up and down, and it will not have any impact on your measurement. However, the rotation of your camera has an impact, and we're actually going to measure the rotation, the amount of rotation from the image itself. So we do not require a relay lens in this case because the light dots are originating from infinity. We can use a very compact design. We can characterize cameras with a large field of view. So you'll see some 120, 125 degree field of view images. We already and also did it with cameras that have around 180 degrees field of view. Of course, there the whole system reaches its limit. And another thing we can use it for is to adjust stereo camera pairs to each other. This is what the device looks like. On the right-hand side, you can see it. So it's very compact. It works at infinity. It covers the large field of views. It's very simple to use. You'll see that in a practical demo at the end. And currently we have a beam diameter of around 75 millimeters. We plan to do a larger version in the future for various purposes, but that's what we currently have. Let's step a little bit into the theoretical background. So we do have a formula that basically describes our diffractive optical element. And the angles alpha and beta are important because that describes the orientation of the diffractive optical element towards the incoming plane wave coming from the expanded laser beam. The wavelengths of our illumination is very important, and so the laser that we use has to have a very stable wavelength. The light is then incident on the camera, and we basically have a 3x3 camera rotation matrix that describes the rotation of the camera towards the diffractive optical element. And as I already mentioned, the translation T here does not matter because we are translational invariant. After that, the whole thing needs to be projected onto the 2D space of our image sensor. And in order to do that, we also need to know or need to measure and determine the focal length of the system and the principal point. These are two example images. On the left-hand side, you see an image captured with a camera that has about 125-degree field of view. On the right-hand side, you see an image that was captured with a camera of about 100-degree field of view. So both of these images do not cause any problem with the evaluation, so we can actually cover that large range of field of view. And as mentioned, we already captured some images. This is, of course, an overexposed image in this case to make it visible or more visible. This is actually captured with a camera that has a 180-degree field of view. And it looks like we can cover most of that field of view with our regular dot grid. And we'll see where we end up. So there's still some development going on and how far we can get to the outside of those large fields. So once we have done all that, we of course need our distortion model. So one of the most important aims here is to measure the coefficients for our distortion formula. In this case, you see a formula that basically only has rotational distortion, and we have the different coefficients that we are going to measure. There are different models, distortion models out there, and the one that's most commonly used, as mentioned, is the OpenCV model, which we will definitely, or we actually do support in our software already. The rotational support, model that you see here is part of that. So the OpenCV model also adds the tangential distortion to it. And that's the pinhole model, and there's also a fisheye model that we also will support so that you can run both types of cameras. So in the end, what we're getting out of this is the principal point. We get the focal lengths of our camera. We get the distortion coefficients. We get the angles, alpha and beta, of the orientation of the DOE towards the incident plane wave coming from the laser. And we also get the three angles, pitch, yaw, and roll of our camera. Let's quickly dive into a practical demonstration. So this is what the whole thing looks like. So you can mount your camera. In this case, it's a cell phone camera, but it can also be an automotive camera. It can be a security camera, whatever is needed. You put that right in front of the diffractive optical element. And just to show you the invariance for translation, I have a little video that I can show. So here we have a cell phone mounted in front of the device, and we shift it left and right, and you see the whole thing does not change. It basically stays exactly the same. The only way it changes is when you are outside of the diffractive optical element. So when the diffractive optical element does not fill the whole field of view of the camera anymore. So here's the comparison with the rotation. There we go. So this is the rotation, and that's actually what we want to measure. So we want to measure how the camera is rotated towards the incident beam, the incident wave. And if you want to adjust stereo camera pairs to each other, that's the important angle that you want to determine. Okay, and then the only thing you have to do in addition is you load your image into the software, then you press an analysis button, and out comes the all the values that I already mentioned. So principal point, the angles, the distortion coefficients, etc. So that's what I wanted to show you, and thank you very much for your attention.